Don't forget about that later on. All righty, ladies and gentlemen, let me do a little attendance here. Lacavian's gone. Melina's gone. Lizeth is gone. Nadia's gone, even though I had her here earlier today. So, okay, I have hope for a few. 1, 2. Wait, how'd you count 7? Oh, you counted me? Thank you. Okay, good. I'm like, man, I'm counting 6 out there. And okay, thank you. Thank you. Normally I don't get counted. I feel so special. Thank you. Oh my gosh. We got dead planaria today. That's not good. That's not good. It's not good to have dead planaria. You need live planaria. Anybody remember planaria lab in biology? Yeah. Yep, we just got some dead ones. Oh, that's not good. Not good, not good. Hey, you're going to have a quiz on Friday, ladies and gentlemen. Stuff on the board here is what will be covered on the quiz. Meaning variables, the 4 variables that affect the gas, what units go with them, things like that. Pressure relationships, okay? Meaning what we're going to teach you today. Temperature conversions, meaning what we're going to teach you today. And relationships, meaning if the line is going up, is that inverse or direct? Or sorry, inverse or direct. If the line is straight or curved, is that constant or non-constant? Okay, so that's what we're going to do. Let me give you a code for the pear deck, ladies and gentlemen. It is XEJ WVF. I don't know what Xeric. Xeric? Xeric elephants joyfully wish victorious flashlights? I don't know what Xeric is. I honestly don't. Never used that word in my life until today.
Containing little moisture.
Containing little moisture?
Very dry. So dry elephants wish for victorious flashlights.
What were the flashlights fighting? Maybe they were fighting darkness.
Maybe.
Okay. That's what I was doing at 3 a.m. in my house, ladies and gentlemen. Okay. All right. Everybody's connected. Here's our first question, ladies and gentlemen, and there are a lot of answers to this. I would like you to name me 2 things that a gas can do that a solid cannot. 2 things that a gas can do that a solid cannot. And again, there are many things here. So you could come up with a lot of different answers here, ladies and gentlemen. Name me 2 things a gas can do that a solid cannot. All right, I'm not going to show the responses. Jeremiah, give me one thing. Good. Gases can take the shape of their container. A solid does not do that. Your desk doesn't change its shape, whether it's sitting in this room, whether it's sitting on the roof, whether it's on the back of a truck. Does not change its shape, no matter what kind of container you put it in. Okay? At least not on its own. People be like, well, you could bend the lengths. Yes, you could. But we're talking about on its own, it doesn't take the shape of its container. Good. Hassan, what do you got for me?
Humans can breathe gas, but not.
Okay. We can breathe in a gas. We can take it into our lungs. We cannot. You can take in solids. Probably not the greatest thing for you, though. Occasionally, we take in dust and things like that, which would technically be a solid. But you're right. Overall, we breathe gases. We don't breathe solids. Good. All right. Savannah, what do you got?
particles don't have volume. Liquids do.
Wait a minute, run that by me again.
Gases don't have volume.
Okay, actually they do have a volume, but they don't have a definite volume. Okay? Gases do not have a definite volume. In other words, gases' volume can change. Okay? Just a slight difference there, but it does make a big difference in that explanation. Okay? Gases' volume can change depending on the container you put them in. Solids will not. Solids stay the same. All right, what do you got, Keanu?
They could fill a room. Gases could fill a room with humans living in it, so you can't try to like avoid the whole a room being full of like full.
Could we fill it with humans?
No, not with humans. Like we are living because we're surrounded by gas.
Okay, so we need gases to breathe.
Like
Or-
gases can fill the room with us still living. But if like a solid filled the room, we would probably suffocate.
Okay. All right, I kind of get what you're saying there. All right. Okay. Well, if the room were filled with liquid and we were in it, that would be very bad for us.
Sure.
For sure. I don't know with the solid, but okay, we can go with that. I kind of get what you're saying. Sabrina, you got one?
The gas particles coming off the lid and solid.
Definitely. Now, are the particles in this desk moving? Yes, but they're not flying around all over the place. They are vibrating back and forth. That's about it. Gas particles flying all over the place. Jays, you got one?
They can fill up an entire space.
Okay, gas particles can fill up an entire space. Good. You guys got most of the ones that I would have given you, ladies and gentlemen. Nice job. Come on. So, one other thing. By the way, gases can flow. What does that mean?
Can move by themselves.
They can move by themselves or by gravity. Okay. In World War II, the Germans used something called mustard gas. Why?
Spread.
Okay, it was heavier, it was more dense than air,
So
and it was poisonous, and it would spread out. But the part about being more dense than air meant that the Germans could sit up on top of a hill while the Allied forces were in trenches, open mustard gas, and it would literally roll down, flow downhill, and fill in that trench. Okay? Now, some gases are lighter than air, and they will float off, but they can move around. Gases take the shape of their container. Whatever container you put them in, they always take the shape of their container. Gases change volumes. Gases completely fill their container. Gases can be smelled. Can you smell a solid?
Roses you can.
Can you smell a liquid?
Yeah.
Yeah, but you know what you're actually smelling in both of those cases?
The gas.
The gases that those things give off. If you are smelling a liquid, get out of the pool, you're drowning. Okay, you and I cannot smell liquids. We cannot take liquids in through our noses and smell them. Okay, that's not how we're set up. But that solid, that rose, that solid, or that liquid, that perfume, they give off a gas that we can then detect. Only gases can we detect.
How do sharks smell blood underwater?
What's that?
How do sharks smell blood underwater?
Well, I can't tell you for sure, but odors can go through the ocean. And then the sharks are able to detect them the same way we can. Now remember, sharks are different. Sharks take in liquids and breathe liquids, right? So they take in the liquid and then they're able to pull the oxygen out of it that they need. You and I can't do that. Okay? So that doesn't mean there can't be scents dissolved in water. For you and I to smell them, they need to become airborne. They need to become liquid. But for sharks and other aquatic creatures, they don't need that. Why? Because they couldn't smell it if they were out of water. So like you and I can only smell it if it's a gas in the air. If a shark were to breach the water, it wouldn't be able to smell the gases in the air anymore. Why? That's not how they're set up to smell. Does that kind of make sense? Okay? So the same way, you and I, there's oxygen in the water. It's dissolved in the water. You and I cannot take that oxygen out of the water and breathe it. Sharks can by taking it across their gills. Sharks and other fish can do that. So they can pull the oxygen out of there. We cannot. We're just set up two different ways. Okay? So again, gases have to be in a vapor form for us to smell them. Gasoline, when you're pumping it into your car, you will smell it. Now, why do you smell it? Because some of it vaporizes and goes to a vapor and we're able to detect it. Same thing with the roast. Some of the things that are inside it give off of gas that you and I can detect then. Perfumes, in the liquid form, we can't smell them. But what we can smell is they easily vaporize, and then we can notice the odors from them. Okay? So again, we are not set up to smell anything other than gases. That doesn't mean that there aren't odors given off by solids and liquids, but that odor still goes into a gaseous state before we can detect it. Okay? Good. All right, take a look at this graph here, ladies and gentlemen. By the way, this is an exact kind of question that's going to be on your quiz. Is that graph constant or non-constant? It is one of these two. And then is it direct or inverse? It is also one of these two. So it could be constant and direct. It could be constant and inverse. It could be non-constant and direct. It could be non-constant and inverse. Tell me what you think that graph is, ladies and gentlemen, and then we'll explain which one it is in just a moment. Okay, let's see how we did. Non-constant and inverse. Non-constant and inverse. Let's make this smaller. Good, good. Ooh, we got a constant in there. Stupid thing. Okay. Now, first of all, ladies and gentlemen, thank you for answering it. Second of all, let's be honest. These two people, maybe you didn't know for sure if it was inverse or direct. On a test, take a guess. You got nothing to lose with guessing. You may get it right, okay? You may get it right. You may not. It's, again, if you get it right, you get a point. If you leave it blank, you lose a point. If you don't answer it, you lose a point for sure. So always try. Okay, so let's start with constant and non-constant. Which one is the line here, Keanu?
Non-constant.
Why?
Because it's curved.
Thank you. Absolutely perfect. This is a non-constant line because this is a curved line. I'm not going to give you any line that isn't clearly curved or clearly straight. I won't give you a line that kind of has a little, no, I won't do that. It's either going to be a straight line or a curved line, okay? So if you look at it and it obviously isn't curved, it is meant to be straight. This one is obviously curved, that means it is non-constant. Okay, so to be direct or inverse, Jace, what does that mean?
If it's a direct, it's going up. If it's inverse, it's going down.
So again, direct going up, inverse going down. This line is going down. So the correct answer, ladies and oops, sorry, wrong one, wrong button, would have been non-constant because it is curved, inverse because the line is going down. Fair enough? Good. All right. So then this one should be easy for you. Okay, so let's talk about a little test-taking strategy here real quick, ladies and gentlemen. These are two questions on the test, and you can't remember what inverse and direct mean. What should you do for both of these lines? Or what is something you could do for both of these lines? If you can't remember what inverse and direct means.
Ask for help.
You could, and again, I would try to give you as much as I could, but let's say you're like, man, Mr. Brand, I don't get what you're telling me. What do I do now? If it were me, here's where you've got two choices. You could guess on both. And you'd be like, all right, I'm going to say that the line that's going down is direct and the one that's going up is inverse. Now, if you do that and you guess correctly, you could get both, correct? But you could also lose both. If I'm not sure and I say, well, you know, they're going in opposite, but I'm going to answer them both direct. What does that mean for my test result? If I put direct for both of them,
1/2.
you get 1 out of 2 right at least. How big a gambler are you? Are you going to gamble and put one that you're not sure of down? Or is it maybe better to say, you know what, I'm going to put direct for both of these because I know I'm going to get 1 out of the 2 right. Again, test-taking strategy that you can use would be to put the same answer down even though you know one of these is going to be wrong, but you know one is going to be right then, correct? So again, if you're confused, that may be a way to go because at least you get 1 point. Now there'll be others who say, you know, I'm going to let it ride, Mr. Brand. I'm going to go for both of them. Go ahead. Go ahead. Okay? But again, some people may be like, you know what? I think I did okay on a lot of it. I'm gonna go for answering it. And other people may be, man, I ain't doing very good on this. Maybe I should get 1 point. Maybe you should. Maybe you should. Okay. How does this line compare to the last one?
Straight.
Straight and so it's basically the opposite of the last one, right? So we're looking at constant and we're looking at direct. Again, just giving you some advice, but again, at least put down 2 answers here. If you only put constant or you only put direct, yeah, you may get that one right, but you're for sure getting the other one wrong. Why not put something down because it's got to be one of the 2?
So what would it look like if it was constant and inverse?
If it were constant and inverse, straight line going down.
Just switch the way it's going.
Back. Constant means the line is straight. Direct means it's going up. Inverse means it's going down. So you can have an inverse and a constant line like that. You could have an inverse and a inverse and a non-constant line like that. Why? This is curved and it's going down. Going down means inverse, curved means non-constant. Going down and constant means it's going down and straight. Okay? So what would this one be?
Non-constant and direct.
Yeah, you're good. So basically you got to separate the 2 things. Is it going up or down? That tells you this. Is it straight or is it curved? That tells you this. And you can be one and either one of the other. You can be curved and going up. You can be straight and going up. You can be curved and going down. You could be straight and going down. And again, that line is still doing what?
Still going up.
Okay, so that makes it
Constant.
nope. Going up is direct.
Oh, okay.
Shape of that line.
It makes it constant or not constant. I mean, it's curved.
Thank you. Yeah. Non-constant because it's not straight, but it's still going up. These are both going up. They're going up in different ways. Okay? Even if you had a line that was like this, that line's still going up, so it's still direct, but now it's straight, so that makes it constant. Any straight line is constant. Any line going up is direct. Okay? And again, you could also just put that down on your periodic table. But again, either memorize it or put it down, either one. All right, that takes care of that, ladies and gentlemen. Excellent. Excellent, excellent, excellent. All right, done with the pair deck. Okay, here's where we're at. We're in the notes. That's not the right side. Let me get to the right side. All right, here's where we're at. Now, yesterday, we showed you the pressure demonstrations for air pressure, something that is around us all the time, but we can't see, we really can't feel, but it's around us. When's the only time you can kind of feel air?
The wind.
The wind. You're driving, stick your hand out the window. You can feel the air. Okay. A fan? Yeah, something like that. But normally we don't get a chance to even notice the air around us. Like right now as we're sitting here, it's not like, oh my gosh, I just got hit in the head by an air particle. No, you don't even notice it, right? Okay, good. With gases, there are 4 things that affect the gas. Pressure, volume, temperature, and amount of gas, correct? Okay, let me ask you this. What is the smallest amount of gas you could ever have?
0.
0. You can't have any less than that, right? You can't have a negative amount of gas, can you? You know what? I owe you 5 gas particles. I'm in the hole. I'm -5. No, you can't do that, right? Okay, what is the smallest amount of space a gas could take up?
0.
0. 0, right? No gas, occupying no space. That's the lowest you can go. You can't be like, you know what? That gas is occupying -5 milliliters. Right? Be like saying I had -$5 in my wallet. Can you have -$5 in your wallet?
Hypothetical.
How?
Hypothetical. It's not actually happening.
How?
I mean, it could be in debt.
You could owe people.
Yeah.
Yes, but you can't have a negative amount of money. Right? You could owe people, that is true. But you can't have a negative amount of money in your pocket. You can't, hey, I'm going to give you -$3. No.
Isn't that just 0 though?
What?
If I say I'm gonna give you $2, that's just 0.
I've tried that before. It doesn't work too well.
I'll tell you what, I'm going to give you a -$2. You know what that means?
You're not giving
You're giving me $2.
I've tried it.
Right? Because that's how you would get a -$2 is by giving $2 away. Don't worry too much thinking about it. It's a bad example. Let's move on. What is the lowest amount of pressure you can have? What is the lowest amount of pressure a gas could ever exert? 0. Now to have a pressure of 0 though, what does that mean for how often it hits the walls? Never. It doesn't. So if it's not hitting the walls, how much gas is there?
0.
None. How much space will it take up? None. What's its temperature?
It doesn't happen.
Should be none, right? But in Celsius, what can our temperatures do?
Go to the negative.
Temperatures can go into negative. That's a problem for gases. Because you can't have a negative pressure, you can't have a negative volume, and you can't have a negative amount of gas. Now, 2 negatives, division, would make a what?
Positive.
Positive. Multiplying 2 negatives would make a positive, right? You multiply 2 negatives, you make a positive. But unfortunately, only temperature can be negative. So since none of the other ones could ever be negative, there's no way to get that back to a positive value, right? So that's where the temperature scale of Kelvin comes in, ladies and gentlemen. The temperature scale of Kelvin is used because Kelvin is what is called an absolute scale. Do you know what that means?
Definite.
Oh, think of an absolute number. What does that mean?
Not negative.
Correct. The absolute value of a number, I should have said absolute value. I shouldn't have said absolute number. The absolute value of a number is always positive. No matter what, it's a positive. Well, this is a scale that has no negative numbers. So what is the smallest temperature you can have in Kelvin?
0.
0, which is perfect for gases. Why? Smallest volume you can have is 0. Smallest pressure you can have is 0. Smallest amount of gas you can have is 0. Now the smallest temperature you can have is 0. But now what does temperature actually measure? Think of the definition we gave you the other day. The one you're going to need for your quiz on Friday. Temperature is the what?
Kinetic energy.
Kinetic energy. So what is the lowest amount of kinetic energy you can have? 0. But they have no kinetic energy. What does that mean? There's no movement. Now you know why temperature is a measure of the kinetic energy. The faster the particles move, the higher the temperature, the more kinetic energy. Well, technically, what's the lowest kinetic energy you can have? 0. And that's when particles stop moving. That is something called absolute 0, ladies and gentlemen. Absolute 0. That is the coldest temperature possible. Why? Because it's when the particles of matter stop moving. Right now, the particles in this desk, even in a solid, they are moving. They're moving pretty fast too, because the room is about 68, 69 degrees. But we could cool it down. And if we got it cold enough, we could get it to the point where those particles stop. Now, we never have. We have never been able to get something that cold. But we're getting close. And we don't actually know what will happen to matter if we get it down to the point where the particles stop. Will the particles then suddenly break apart and cease to exist and the atoms somehow change? We don't know. But we do know that if you could stop it, that's as slow as it can go. Ever. Ever. Okay? For Kelvin, we use K as a symbol. We don't use a degree sign. You don't ever say degree Kelvin. Okay? And ladies and gentlemen, these are the two formulas that you need to write down on your periodic table for how you can convert to Kelvin from Celsius and to Celsius from Kelvin.
When converting, do sig figs also matter?
Yes and no. The rules for sig figs are different when adding and subtracting. It's not based on how many there are. It's based on the least precise measurement. And technically, I'm rounding this number a little bit. It should be 273.15. Should be. We're not going to do that. So I'll show you what we would do with our numbers in a minute. I'm not going to worry too much about sig figs when you're converting temperature, though. Okay? I'm not going to worry about sig figs when you're converting temperature. Okay? But that is a good question. So to get from Celsius to Kelvin, all we do is add 273 to it. That's it. And to get from Kelvin to Celsius, all we do is subtract 273. Okay? So these are our formulas. What temperature does water freeze at in Celsius? What?
Below 0?
Well, at 0.
Yeah.
So if it's 0 Celsius, what's the temperature in Kelvin?
273.
273. What temperature does water boil at?
In what?
In Celsius, I'm sorry. Celsius. Because we're not going to do any conversions with Fahrenheit or anything like that.
Is it 100 or
It's 100. So what temperature would that be in Kelvin? 373. So I want you to notice something here, ladies and gentlemen. 0 degrees Celsius. Okay, here we go. 0 degrees Celsius, and I need a marker thing, is actually 273, correct, Kelvin? 100 degrees Celsius is 373 Kelvin, correct? How much did we go up by here? 100. How much did we go up by here?
100.
Now, 1 Kelvin is not equal to 1 Celsius, but a change of 1 Kelvin is going to be a change of 1 degree Celsius. So however much this changes, this would change the same amount. Okay? Now, what is the lowest temperature that we can have in Kelvin? 0 Kelvin. I'll do that to make sure we understand that's a 0. What is that in Celsius?
Negative 273.
That's as cold as it could ever get. So somebody goes, well, no, it could get to minus 300 Celsius. No, it can't. Why? Because at 0 degrees Celsius, the particles stop moving. To get to negative 300 degrees Celsius, the particles need to have a negative kinetic energy. They cannot do that. They cannot do that. Okay? This is cold. In Fahrenheit, like we report the weather outside on a normal day, like today is about what? 30 some degrees? 25, 28, somewhere in there. This is negative 459 Fahrenheit.
That could kill you.
First of all, no.
No?
You would be dead long before then.
Yeah.
The reason being, when you get down to about minus 181, 183 degrees Celsius, the oxygen gas will be forming a liquid. It will go and it will land on the ground and we will have nothing to breathe. We will die because of lack of oxygen in the air. At minus 200 degrees Celsius, that liquid oxygen will now turn into solid oxygen like ice, and we would have no way of breathing it again either. And we're still not down to minus 273 yet. Still a long way to go. And you know how in winter they'll say, oh, if you go out today, it's like minus 60 outside. Exposed skin will get frostbite in seconds or in minutes. Minus 459 degrees Fahrenheit, you are getting frostbite almost instantly. You will not be able to stay warm enough to survive. Not to mention you would have nothing to breathe. Okay? So again, people say, well, can we survive if it gets that cold? No, we cannot. We cannot. Okay? There'd be no oxygen to breathe. There would be way too cold of an environment for us to survive. Yes, sir.
I just looked up how cold is the vacuum of space, and it's not even 0.
How cold what?
How cold the vacuum of space is, and it's not even 0.
Not even 0 Kelvin? No.
It's 2.7 Kelvin.
Yeah. Which means the particles are still moving. Not very much, but they're still moving. Okay? So again, even in the emptiness of space, it doesn't get down to absolute 0. Doesn't get down to absolute 0. Yes, sir.
This is kind of out of topic, but I heard that NASA discovered a planet with life in it. It's like cities. And I don't think you heard.
If they ever found that, we would all know about that. If there was actually life. Like with cities and things?
Yeah, they said it was city lights.
No.
So it's not true?
No. NASA has a hard time finding even microorganisms. Now, is it possible that there's some planet out there that maybe, yes, possible, I don't know. The universe is way too expansive for us to say it's not possible. But no, NASA has not found something like that, because if they had, it would be all over the news. It would be all over mainstream. NASA would be celebrating like crazy, finding something like that. No, you might have heard something like that on the internet, or maybe somebody embellished something like NASA found water on a planet and it could support life, to somebody turning into, oh, there's life on another planet. No. NASA has not found that yet. Okay? NASA has not found that yet. All right. So, ladies and gentlemen, here we go. All right. Along with converting temperatures, we are also going to need to convert pressures in this unit. But let's go back to temperatures. 50 degrees Celsius, to convert it into Kelvin, we're going to add 273 to it. What do we get if we add 273 to 50? We get 323 Kelvin. What if we add 85 degrees Celsius? Again, we're going to add 273 to it. I'm not expecting you to do this in your head, ladies and gentlemen. I would be expecting you on a test to use a calculator. I would be expecting you on a quiz to use a calculator. What would we get if we added 85 and 273? We'd get 358. Even if we take a number like minus 50 degrees, we still just add 273 to it. Now, this number that we get is going to be less than 273, but it's still what? 223, which is a perfectly fine number in Kelvin. The one thing you can't have, though, is I can't say, well, what if it was negative 300 degrees Celsius? You would end up with a negative number in Kelvin, and you cannot do that. Cannot do that. Okay, what if we were doing the other way? 425 Kelvin. Well, you're going to take 425, you're going to subtract 273.
152.
We get 152. 185 Kelvin. Minus 273.
Negative 88.
Wait a minute. Can we get a negative number?
Celsius.
In Celsius, yes, we can. In Celsius, yes, we can. We can't get a negative number in Kelvin. Okay? What about 1245? Well, again, you just subtract 273 from it.
972.
972. There you go, ladies and gentlemen. Questions? All right. So, STP. Okay? There are a set of conditions out there that are called standard temperature and pressure. And it's basically just a baseline, giving us something to compare to. Hassan, what sport do you like? Soccer. For an average soccer player, how many goals do they score in a year, would you say?
The most that's ever been scored is 91 in a year.
91 in a year. Okay, what would be considered around average? Do you know? Okay. So if someone scores over 30 goals in a year, they're probably a pretty good player. If you score less than that, maybe not. But maybe you're playing a position that you don't have to, right? But still, that's a baseline that we could say, okay, good players should do over this, right? In basketball, maybe it's scoring 20 points a game. If you score over 20 points a game, you're considered pretty good. If you score under that, you're not. There's a line somewhere, right? Well, here's our line for gases. At 0 degrees Celsius, or 273 Kelvin, standard pressure would be 760 millimeters of mercury. It would be 14.7 psi, it'd be 101.3 kPa, and it would be 1 atmosphere. So this is just kind of a baseline for things, okay? If you're under 3 atmospheres of pressure, you're under quite a bit of pressure. That's 3 times what we're under right now. Go underwater, 30 feet below the water. You're going to be under 3 atmospheres of pressure, okay? So you can go and put yourself in an environment where you might be more or less in this. Go to Denver. Denver's the mile-high city. You're going to be well under 1 atmosphere of pressure in the mile-high city because you're a mile high into the air. There's less air on top of you, okay? So this is a baseline. But what this also is, ladies and gentlemen, is 4 ways of saying the same exact thing. 4 ways of saying the exact same thing. If I have $1, how can you have $1 in only one kind of coin, Jeremiah? Pick a coin. How many of them would you have to have? Quarters. You'd have to have 4 quarters. Sabrina, how many pennies would you have to equal $1? 100. Keanu, how many nickels? Get this right, or I'm going to my drawer and getting some nickels for you. We're doing some exchanging.
I'm blanking.
It's 3. So I'm going to go get 3 nickels, and you're going to give me $1 for those 3 nickels, okay? Why not?
Because 20.
Okay, it's 20. It's 20. How many dimes?
50.
How many? How many?
40.
How many? 40? Wait a minute. I got $1 here. You give me 40 dimes for it. Okay? I got $1 right here. Give me 40 dimes for it. It's a good thing you don't. You know why? You'd be giving me $4. Dimes are worth 10 cents. There's 10 of them in $1. 10 of them. You guys, I want to be your banker someday. I really do. I really do. Those who are not good with math, I would love to be your banker. All right. How many half dollars?
2.
2. 2. Okay? How many dollar coins? 1. $1 coin, 2 half dollars, 20 nickels, 10 dimes, 100 pennies, 4 quarters. All equal how much?
$1.
$1. I don't care how you say it. All of them have different numbers. 4, 100, 10, or 20, 10, 2, 1. All have different units with them, right? But they all mean the same amount. Same thing here. All 4 of these mean exactly the same amount of pressure. Exactly the same amount. Okay? All right? Exactly the same amount. And we can use them to go from one unit of pressure to another. Now we're going to show you how to go from one unit of pressure to another unit using these, ladies and gentlemen. Now you're going to have a hard time typing in these boxes, so don't try. Just let me go over this with you and let me show you, because if you try typing in there, it's going to be a pain in your butt, trust me. All right, let's begin with this. That problem said you have 3.11 ATMs. That's atmospheres. And we want to know how many, was it millimeters of mercury? Yes, thank you. Okay, now before I can do this, ladies and gentlemen, I have a simple math question. Who's good at math?
Sometimes
Okay, who's not good at math? Good. Hassan, this one's for you. What's 7 divided by 7? Good. Excellent. Wonderful. Jeremiah, you good at math? No. Okay, Jeremiah, what's minus 21.5 divided by negative 21.5? Negative 21.5 divided by negative 21.5 equals what? You said you weren't good at math.
Oh, that's right.
Yes, that's right. Okay. Sabrina, x plus 2y divided by x plus 2y equals what? You got it. Why? Anytime you divide a number by itself, you get 1. You get 1. Any value over the same value is 1, right? Okay. Now the real hard question. You ready, Savannah? Okay. 4 quarters over $1. This was a hard one. I said that. Jays?
1.
Still 1. Isn't this the same as this? So then that means it's 1. Right? Okay. Chance to redeem yourself here, Savannah. $1 over 4 quarters equals? Yeah. It doesn't matter which one's on top. Doesn't matter which one's on the bottom. Because they're equal, they both equal 1, right? Okay, good. So now, I'm going to take 3.11 ATM, and I'm going to multiply it by something. We're going to multiply by a conversion factor, okay? Now, on the top of the conversion factor, I'm trying to get to millimeters of mercury. So on top, I'm going to put this number. Okay? On the bottom, I need to put a number that is equal to this, but the number has to be an ATM. What number would I put on the bottom? Where did I get this from? Right there. Aren't all 4 of these equal to each other? Then you know what? I can use either one on the top and I can use either one on the bottom. Why did I put the ATM on the bottom? Well, here's why. Look at what these units do. This cancels that. They cancel each other out. What unit am I left with? What's the only unit that I haven't canceled out here?
Millimeters of mercury.
Millimeters of mercury. That's what I was trying to get into. This is what we call a conversion factor, ladies and gentlemen. Because these two things are equal to each other, I can make a conversion factor out of them. Now, if I said 50 cents and $1, is that correct? Well, it's not correct. I can't use that as a conversion factor. Why? 50 cents does not equal $1. 2 quarters does not equal $1. These have to be equal for me to do this. These are equal. How do I know? Right up here it tells me. Okay, take 3.11 times 760 and tell me what you get.
2,363.6.
That is how many millimeters of mercury would be in 3.11 atmospheres. That is how we convert from one unit to another. That is how we convert. Now, there's one last thing, ladies and gentlemen. How many sig figs in this number here, Keanu? 3.11.
Oh, 2, 3, sorry.
Which one?
3.
Good. 3 sig figs. The 3, the 1, and the 1, right? So how many can I have in my answer? I can only have 3 sig figs in this answer. Okay, what's the third sig fig in this number?
6.
Yeah, now we're going back to something we did a long time ago, right? I'm sorry, but it's been a long time for this, right? Okay. The number after the 6 is a 3, correct?
0.
So do I leave that 6 or do I move it up to a 7? The number after is a 3. So I leave that 6, right? But what do I got to put here?
0.
A 0. Why? Well, this is the thousands place, correct? This has to still be the thousands place. I need to put a number in here that is not significant, but holds that place. Why is this 0 not significant? There's no decimal. Very good. You guys are remembering this stuff. That's awesome. That is awesome. So occasionally we got to be careful. That's the only thing that can mess you up here is sig figs. That's it. That's the only thing. Okay? All right, let's do one more and then we'll call it good for today, ladies and gentlemen. And then tomorrow I will give you a chance to practice this. All right. Oop, wrong one. So let's convert 85.0 kPa to PSI. 85.0 kPa into PSI, right? Okay, here's kPa, here's PSI. I take the number that I'm trying to convert and I begin with it, 85.0 kPa. Put a time sign and a fraction bar. Something's got to go on the top, something's got to go on the bottom from up here. What goes on the top or what goes on the bottom? Jeremiah, give me one or the other. Goes where? Okay, so if I put the 101.3 kPa up here, does this allow me to cancel it out, Jeremiah? So what does that mean? Thank you. That's the worst that'll happen. You accidentally put it in the wrong spot and then we move it. So we're going to put it on the bottom. 101.3 kPa. This way the kPa's will cancel, right? Okay, I'm trying to get to PSI, so what do I put on the top? Look up here. How many PSI? 14.7 PSI. Now, the math here is a little bit more difficult, but we're going to take 85.0 times 14.7 and then divide it by 101.3. Why? Because that's how we can handle this fraction. We multiply by the number on top and divide by the one on the bottom. What do we get?
12.3, and that's the sig fig portion.
So we probably got 12.3, 1 something, something like that. Fine. We only want 3 sig figs. That's 3 sig figs. The unit is PSI. That is what we are going to be practicing tomorrow because that is going to be on your quiz on, I have to check. I'll double check. I need to see if it's on your quiz. Now, here's the other thing, ladies and gentlemen. I will give you these. You don't need to write these down. I will always give those to you. Okay? Always, always, always. Questions? All right, good. Nice job today, ladies and gentlemen. Nice job.